All right, so today we're going deep on generative AI. We've got this Generative AI Handbook to guide us,
Right.
and it seems like you're really into the cutting edge stuff.
Yeah, for sure.
Like how these models actually work,
Uh-huh.
how to optimize their performance, and
Mhm.
even like how to sort through all the resources out there to like really learn about them.
It's a lot.
Yeah, it's a ton.
And actually, that's kind of why this handbook is so cool.
Right.
It's like a dynamic guide,
Yeah.
you know, constantly pointing to the latest research breakthroughs.
Yeah, I love that.
Hey,
It's like a syllabus that's always updating.
Exactly.
Speaking of breakthroughs, the handbook kicks off by painting a picture of the AI landscape.
Okay.
And wow, things have been moving fast.
It's been a whirlwind, seriously.
Yeah.
Just like 18 months ago, ChatGPT was this, like, novel concept.
Yeah.
Now you've got Meta, Google
Yeah.
racing to release their own large language models.
Mm-hmm.
You have new players like Mistral, Anthropic, coming up as serious contenders.
Yeah.
It's like AI is everywhere you look.
It really is. It's crazy.
It's like it went from like science fiction to reality,
I know.
like overnight.
Remember when we used to be amazed by like a computer beating a chess grandmaster?
Yeah.
And now you've got AI making art,
Well,
writing code, composing music.
it's incredible, right?
It really is.
And that's just the start, you know?
Right.
What's interesting is this rapid progress. It's sparking all this discussion about,
Yeah.
you know, the economic side of AI,
Right.
especially jobs, the job market.
Mm-hmm.
Some experts are like, oh, AI is going to create all these new industries, new jobs. Others are worried about, you know, people losing jobs.
It's a big question for sure.
It is.
And it kind of highlights this need to really understand how these AI tools work.
Yeah.
It's like the author says, you want to be a true innovator,
Uh-huh.
you got to go beyond just driving the car.
Right.
You got to learn how the engine works.
Learn the mechanics.
Yeah.
And that's where this handbook really shines.
Okay.
It gives you that roadmap to like developing that deep understanding. And it starts with the math, the foundations.
Okay, so calculus, linear algebra.
Yeah.
I know some people hear that and they're like, oh, no.
Yeah.
But the handbook's not saying you need to be a math whiz.
No, not at all.
It's more about intuition, right?
You're building that intuition.
Getting the big picture.
Yeah.
And there are resources out there that help with that, right?
Oh, yeah, for sure.
Like the 3 Blue 1 Brown YouTube series.
That's a great one.
Yeah, it explains things visually.
Yeah. So you can really like see the
Say
content.
gradients, the chain rule, the
wow.
analysis.
It makes it much easier to grasp, even if you're not, you know, a math expert.
So it's not about getting bogged down in the formulas.
Right.
It's more about like understanding visually, intuitively.
Yeah, exactly.
Okay, so beyond the math, the handbook dives into a few other foundational ideas. And it starts with something we all encounter every day, time series analysis.
Yeah. You might be surprised how relevant that is.
Right.
Think about weather forecasting, right?
Okay.
Today's temperature helps predict tomorrow's.
Yeah.
That's like an autoregressive model in action.
Okay.
And the same principles, they apply to how large language models predict the next word in a sentence.
That's a great way to put it.
It's like it connects to something we can all relate to.
Yeah.
It's not just abstract equations.
Yeah.
It's about patterns,
Yeah.
predictions.
Right.
It's stuff we do all the time, whether we realize it or not.
And then there's online learning,
Yes.
which is like adapting to each new piece of data as it comes in.
Yeah, like learning on the fly.
Right, like constantly updating your understanding.
Exactly.
And the handbook author, they highlight a really cool point.
Yeah.
With good learning algorithm,
Yeah.
the order information's learned and
Uh-huh.
it doesn't actually matter.
Right.
Gradient descent can handle it.
Yeah. Powerful stuff.
So it's not like we need to feed these models information in a specific order.
No.
They're much more flexible, adaptable than we might think.
Absolutely.
Okay, so we've got time series analysis.
Yes.
We've got online learning.
Uh-huh.
And now let's talk about something that's been getting a lot of attention lately.
Okay.
Reinforcement learning.
Yeah. Reinforcement learning.
A lot of us have like this vague idea of what it is.
Right.
But what's the core concept here?
So think of it like training a dog.
Okay.
You give the dog a treat when it does something right.
Mm-hmm.
And over time, it learns to repeat those actions.
Right. Positive reinforcement.
Exactly.
Shut up.
And in reinforcement learning, we're doing something similar with AI models.
Okay.
We define a reward function,
Okay.
and the model learns to maximize those rewards
Okay.
by taking actions that lead to good outcomes.
So it's like we're giving the model a set of incentives.
Yeah, yeah.
And it figures out how to like game the system to get those rewards.
Precisely.
Okay. I like that.
And this is super important when you're fine-tuning large language models to align them with, human preferences.
So it's not just about letting these models run wild.
No.
We're actively shaping their behavior. We're defining what good looks like.
Right.
And rewarding them when they get it right.
Exactly.
Okay, so we've covered some of the high-level foundations of AI.
Right.
Now let's get to the heart of it.
Okay.
Neural networks.
Neural network.
I think most people have heard that term.
Yeah.
But, what are they really?
So they're the building blocks of modern AI.
Okay.
They're inspired by the way the human brain works with these interconnected nodes, like neurons, that process and transmit information.
So it's like we're building artificial brains using code.
That's a good way to think about it.
Yeah.
The handbook actually points to this classic blog post by Andrej Karpathy, where he built a basic neural network from scratch using Python.
Wow, coding a brain from scratch? That's impressive.
It is.
But we're not just talking about, simple neural networks here, right?
No.
We need something more sophisticated.
We need to handle the complexities of language.
Yeah.
So we use what are called recurrent neural networks.
RNN?
Yeah, or RNNs.
Okay.
These are like neural networks with memory.
Okay.
So they can process sequences of information.
Like sentences.
Exactly.
Okay.
By remembering what came before.
So it's like how we use context to understand a sentence.
Exactly.
These RNNs, they have this built-in mechanism for keeping track of the previous words.
Yeah.
And using that to interpret the current word.
Exactly. That's it.
Okay.
And this ability to process sequences, this is what makes RNNs so good for tasks like language modeling, machine translation, even speech recognition.
That makes sense.
Yeah.
But the handbook also mentions LSTMs and GRUs.
Oh, right.
What are those all about?
So these are special types of RNNs that have even more sophisticated memory mechanisms.
Oh, wow.
Think of them like super-powered RNNs.
Okay.
That can handle much longer sequences of information without losing track of the context.
So they're like memory champions, able to remember these long stretches of text or speech and use that information to generate more coherent and meaningful outputs.
That's a great way to put it.
Okay.
And these advancements in RNN technology, they've been crucial for the development of the large language models that we see today.
Okay.
But before we jump into the complexities of those models, there's one more fundamental concept we need to talk about.
Okay.
Embeddings.
Embeddings.
Yeah.
Okay. This is where things start to get a little mind-bending for me.
Okay.
So,
okay.
Help me out here.
So imagine you could represent every word in the English language as a point in space.
Okay, so each word gets its own little coordinate.
Exactly.
And some sort of word universe.
Yeah, like a word universe. And the location of each word in that space, it's determined by its meaning.
Okay.
So words that are similar in meaning, they'd be clustered together.
Okay.
Words with opposite meanings would be far apart.
So it's like a map of the English language where the distance between words reflects their semantic relationships?
Precisely.
Okay.
And these spatial representations of words, these are what we call embeddings.
Okay, so instead of thinking of words as just strings of letters, we're thinking of them as points in a multidimensional space.
Yes.
And their position in that space tells us something about their meaning.
Exactly.
Okay, I think I'm starting to get it.
Good.
So these embeddings are fundamental to how modern language models work.
They are.
They use these embeddings to represent words, understand relationships between words, and generate text that's both grammatically correct and semantically meaningful.
That's it.
This is fascinating. I'm starting to see how all these different pieces fit together.
Yeah, it all starts to come together.
We've got the mathematical foundations, the basic building blocks of neural networks, and now this idea of embeddings, which allows these models to understand language in a much deeper way.
Exactly.
This is awesome.
It is. And these building blocks, they set the stage for understanding the more complex architectures behind modern language models, which we'll explore in more detail in the next part of our deep dive.
I can't wait. This is already blowing my mind.
It's a lot to take in.
I'm eager to hear more about how all these pieces come together to create the amazing AI systems that we see today.
We'll get there.
Awesome. Okay, so we've laid the groundwork, neural networks, embeddings, all that good stuff.
Yeah.
And now let's dive into the the real nitty-gritty of modern language modeling.
It sounds good.
Where do we even begin with that?
So a good starting point is tokenization.
Tokenization. Okay.
Imagine you're teaching someone a new language.
Yeah.
You wouldn't just like throw a whole dictionary at them, right?
No.
You'd break it down into smaller, more digestible chunks.
Like, you'd start with the alphabet.
Right.
And then maybe some basic vocabulary.
Exactly. Tokenization does something similar for AI.
Okay.
It breaks down text into these smaller units called tokens.
Okay.
Which could be words, parts of words, or even individual characters.
Okay.
And this is where it gets kind of interesting.
Yeah.
We don't always tokenize by whole words.
Oh, okay.
Why not?
Yeah, I mean, wouldn't that be simpler?
Well, you think so, but think about words like misspellings.
Yeah.
Or like brand new slang terms.
Okay, yeah.
If a model hasn't seen those exact words before, it needs a way to like make sense of them.
Right, right.
So it's like giving the AI the ability to decode new words based on familiar parts.
Like, breaking it down.
Yeah, breaking it down.
So it can figure out what the word means,
Exactly.
even if it's never seen that exact combination of letters before.
Precisely.
Okay.
By breaking down words into subword units,
Okay.
the model can handle variations, misspellings, even completely new words.
So it can adapt.
Yeah.
As language itself changes.
Exactly.
Okay, so we've got these tokens.
All right.
And now we need to, give the model a sense of their order, right?
That's where positional encoding comes in.
Positional encoding, okay.
Imagine you have a sentence like, the cat sat on the mat.
Okay.
If you just scrambled the words, the meaning would be completely lost.
Right. Word order is everything.
Exactly. Word order is crucial.
Okay.
So positional encoding is like giving each token a number tag.
Okay.
That tells the model where it falls in the sequence.
Okay.
But it's not just like 1, 2, 3 tags.
Yeah.
It's more sophisticated.
Okay.
Like using sinusoidal functions.
Well, wow.
Which gives the model like this nuanced understanding of word order and relationships.
Okay, so we've got the language broken down into these tokens.
Yeah.
We've given those tokens a sense of order.
Uh-huh.
Now, how do we actually train these, massive language models?
That's a great question.
It seems like, I don't know, like a Herculean task.
It's a big task.
Yeah.
And the handbook talks about these pre-training recipes.
Okay.
Which I think is a good analogy.
Okay.
Imagine baking a cake, right?
Okay.
There are countless variations.
Yeah.
Depending on your ingredients.
Yeah.
Baking time, the oven you use.
You could have a simple vanilla cake or a decadent chocolate masterpiece.
Exactly.
Right.
Pre-training a language model is kind of similar.
Okay.
There's so many choices.
Yeah.
About the architecture, the data, the training algorithms, all that.
So it's a complex process.
It's a complex.
You're feeding the model all this text data.
Tons of data.
And then adjusting its parameters so it can learn
to
predict the next word in a sequence.
It's like giving it a crash course in language.
Right.
Exposing it to this vast library of text.
Yeah.
So it can absorb the patterns, the nuances of how we communicate.
Okay.
And the choices you make during this pre-training phase, they have a huge impact on the model's performance and what it can do.
It's where the magic happens.
It is.
But these models are so big.
They are massive.
I can't even imagine the computing power it takes to train them.
It's mind-boggling.
Yeah.
You're talking about a level of computational power that's just, it's crazy.
Yeah.
It's like building a supercomputer just for AI.
And one of the key techniques for handling this is distributed training, right?
Distributed training, yeah.
Okay, break that down for me.
Okay, imagine you have this giant jigsaw puzzle.
Okay.
Instead of trying to put it together yourself, you invite a bunch of friends over, each working on a different section.
So you're dividing the task.
Yeah, divide and conquer.
We're working together to get it done.
That's the idea. Oh. Distributed training involves breaking down the model and the data into smaller pieces.
Okay.
And spreading them across multiple computers.
Okay.
So they can work in parallel.
So it's like creating a super brain out of many smaller brains.
That's a good way to think about it.
Working together to solve this complex problem.
Yeah, exactly.
There's a specific technique, right?
So one of the popular techniques is called fully sharded data parallelism.
FSDP.
Yeah, or FSDP.
Okay.
It's a mouthful.
Yeah.
But the idea is to make that training process more efficient
and
scalable.
Okay.
by distributing the workload across all these machines.
This is also fascinating.
Yeah.
But like with all this talk about scaling and computing power,
Yeah.
I'm curious, how do we know when a model is actually good?
That's a great question.
Like, is there a way to predict how well it's going to perform before we invest all this time and resources into training it?
So this is where scaling laws come in.
Scaling laws.
It turns out there's this predictable relationship
Okay.
between how well a large language model performs,
Yeah.
the amount of data it's trained on,
Okay.
and the computational resources used to train it.
So it's like a recipe for AI success.
Kind of. Yeah.
If we know the ingredients and the size of the oven,
Uh-huh.
we can predict how delicious the cake will be.
That's a good analogy.
Okay.
These scaling laws, they let researchers estimate how well a model will perform,
Okay.
even before they train it,
Oh, wow.
which helps them optimize the process
Right.
and make the most of those precious computing resources.
So it's incredibly valuable.
It is.
It's like having a crystal ball.
Yeah, not quite a crystal ball,
But it's close.
but it's a powerful tool.
Yeah.
But even with all this computing power and these clever techniques,
Yeah.
these models can still be pretty resource intensive.
Right. They're huge. And they're only getting bigger.
That's true.
So we need to make sure they can actually run on the hardware we have.
Exactly. And that's why there's been a lot of focus on making them more efficient.
Efficiency.
Yeah.
Okay.
And one of the interesting approaches for that
Yeah.
is called mixture of experts,
Mixture of experts.
or MOE.
Okay.
Imagine you're building a house.
Okay.
You wouldn't hire a plumber to do the electrical wiring,
Yeah.
right?
No, you'd want specialists.
Exactly. Specialists for each task.
Yeah.
MOE applies that same principle to AI.
Okay.
Instead of having the entire model process every single input,
Yeah.
it breaks down the task
Okay.
into these smaller subtasks
Okay.
and activates only the relevant experts.
So it's like having a team of specialized AI agents, each with their
Yes.
own area of expertise,
Uh-huh.
working together
Yeah.
to solve a complex problem.
That's a great way to think about it.
Okay.
And this specialization,
Yeah.
it lets MOE models be much more efficient than those traditional models.
Because they're not wasting resources.
Right. They're not wasting computational resources
Right. They're not wasting computational resources.
on tasks that don't require their specific expertise.
Exactly. Exactly. Okay. So we've trained this massive model.
Yeah.
We've made it more efficient.
Uh-huh.
Now what?
Well, now we can start to fine-tune it.
Fine tuning.
Yeah.
Okay.
It's like taking a raw diamond and polishing it.
Okay. So we're taking these like already powerful models
Yeah.
and we're giving them specialized skills.
Precisely.
Okay.
And one of the most popular techniques is called instruct fine-tuning.
Instruct fine tuning. Okay.
Think about like teaching a dog to follow commands.
Okay.
You give it specific instructions,
Yeah.
reward it when it obeys.
It's all about reinforcement.
Right. Positive feedback.
Yeah.
Instruct fine-tuning does something similar with language models.
Okay.
We give the model a set of instructions,
Wait, like what?
like translate this sentence into Spanish,
Oh.
or write a poem about the ocean, and then we fine-tune its parameters
Mm-hmm.
so it can learn to follow those instructions really well.
So it's like giving the model a crash course in specific tasks.
Yeah.
A crash course. Like we're teaching it to be a multilingual translator, a creative writer, even a coding expert.
Yeah, got it.
Yep.
And this technique's been super successful
Yeah.
at adapting these like general purpose language models
Right.
to all sorts of specialized tasks.
This is amazing.
It is.
But I'm also curious about like the cost of all this, the
Yeah.
computational cost of fine-tuning these massive models.
Right.
It sounds like it could be like pretty resource intensive.
It can be, especially for very large models.
Yeah.
But that's where techniques like low-rank adapters come in.
Low rank adapters or LoRaWA.
Yeah, Laura.
Okay.
Think about renovating a house.
Oh, okay.
Sometimes you just need to repaint the walls.
Yeah.
You don't need to tear down the whole structure.
Right. A targeted approach
Exactly.
can be much more efficient.
Exactly. LoRa works in a similar way.
Yeah.
Instead of updating all the parameters of the model
Yeah.
during fine-tuning,
Mm-hmm.
it focuses on updating just a small subset
Okay.
that are most relevant to that specific task.
So it's like a surgical strike,
Yeah, surgical strike.
targeting the areas that need improvement
Exactly.
without wasting resources on the rest of the model.
That's a great analogy.
Okay.
And this targeted approach makes LoRa much more computationally efficient,
Okay. That makes sense.
especially for those really large models.
Yeah. Okay. So we've got instruct fine tuning.
Yeah.
We've got LoRa.
Uh-huh.
Any other fine tuning techniques that like stand out?
Well, remember we talked about reinforcement learning earlier?
Yeah. With the dog and the treats.
Right, right.
Okay.
Well, it turns out that's a powerful tool for fine-tuning as well.
Okay.
Specifically, there's this technique called reinforcement learning from human feedback.
RLHF.
Yeah, or RLHF.
Okay.
Which is all about aligning language models with human preferences.
Okay, I'm intrigued. How does that work?
So it involves training a separate reward model
Okay.
that learns to judge the quality of the language model's outputs
Okay.
based on feedback from humans.
So, like, it's got a panel of judges scoring its performance?
Yeah, kind of.
Okay.
And this feedback then guides the fine-tuning process.
So it's like giving the model a personal coach.
Yeah, a personal coach.
Helping it to refine its skills, perform at its best.
That's a great way to think about it.
Okay.
RLHF's been super successful at improving the quality and the safety of these language model output.
Making them more aligned with, like, human values and expectations.
Exactly.
This is all so fascinating, but I'm also realizing that, like, fine-tuning these models, it's not like a one-time thing.
No.
It's a continuous process.
It's ongoing.
As our needs and preferences evolve, we're going to need to keep refining these models.
We have to keep up.
To keep up.
Yeah.
Okay, so beyond fine-tuning, there are other ways to enhance the capabilities of these models, right?
Absolutely.
Like context scaling.
Context scaling. Yeah.
Okay, now that sounds intriguing.
It's an interesting one.
What's that all about?
So think about how much information you can hold in your mind at once.
Okay.
You know, we have limited working memory.
Yeah, you try to juggle too many ideas at once and it just leads to confusion.
Exactly, overload.
Yeah.
And language models face similar limitations.
Okay.
They have this fixed context window, which limits how much text they can process at any given time.
Okay.
Context scaling is all about expanding that window, allowing the model to handle longer, more complex inputs.
So it's like giving the model a bigger canvas to work with.
Yes, a bigger canvas.
It can see the bigger picture, generate like more coherent and relevant outputs.
That's a great way to put it.
Okay.
And this expanded context window, it's super important for tasks that require like understanding long documents.
Okay.
Engaging in like complex conversations. Or generating creative text formats like stories or scripts.
This is incredible.
Yeah.
It's like we're constantly pushing the boundaries
of
what these models can do.
Pushing the limits.
Giving them more power to process and generate language.
It's an exciting time to be in this field for sure.
It is, but with all this power comes responsibility, right?
Of course, of course.
We need to make sure we're using these models in ways that are safe, ethical, and beneficial to society.
Those are crucial considerations.
Okay, let's shift gears for a moment. Let's talk about two other techniques that are often used in conjunction with fine-tuning. Distillation and merging.
Distillation and merging, yes. These are fascinating techniques for leveraging the knowledge and capabilities of multiple models. Distillation is kind of like having a brilliant professor condense all their years of knowledge into a set of like concise lecture notes for a student.
So it's about transferring knowledge from a larger, more complex model to a smaller, more efficient one.
Exactly. And this can be super valuable for making these powerful models more accessible, more deployable on devices with limited computational resources.
So it's like creating a pocket version of a supercomputer.
I like that analogy.
Allowing us to access its power in a more like convenient and portable form.
That's it.
Okay, and then there's merging.
Merging, yes.
Which is, I don't know, a little bit more of a Wild West technique.
It's a little less controlled, I'd say.
Yeah.
Mostly used in like open source communities.
Open source, so it's like this collaborative effort.
Very much so.
Where developers are sharing their models and like combining their strengths.
Exactly.
Okay.
And the way they do this is surprisingly simple.
Okay.
They essentially average the weights of these different fine-tuned models.
Okay.
Creating a new hybrid model.
A hybrid.
Yeah.
So it's like taking the best parts of two different brains.
Right.
And creating a super brain.
That's a good way to visualize it.
Okay.
And the results can be quite impressive.
Yeah.
Merged models They often outperform their individual counterparts.
So it really shows the power of collaboration.
Absolutely.
Like knowledge sharing.
It's crucial.
In the AI community.
Yeah, the community aspect is huge.
This is all so inspiring.
It is.
It's like, I don't know, we're witnessing a new era of collective intelligence.
Yeah.
Where humans and machines are working together.
It's exciting.
To push the boundaries of what's possible.
It's amazing to see.
It is, but with all this talk about training and fine-tuning, let's take a step back and talk about how we actually evaluate these models.
Right, we can't just assume they're good.
Right, just because they're big and complex.
Exactly.
We need ways to measure their capabilities.
We need to see how they stack up.
See how they perform?
Yeah.
Like, how do we do that?
So it's like having an AI Olympics.
Okay, an AI Olympics. I like that.
To see which model takes home the gold medal.
What are the events?
Well, there are different types of evaluations.
Okay.
Each designed to test like a different aspect of the model's abilities.
Okay.
Some focus on specific tasks, like translation question answering.
Okay.
Others assess more like general capabilities,
Or what?
like language fluency, reasoning, common sense, things like that.
So it's like different events to test the models, like speed, agility, overall intelligence.
Exactly.
And some of these events involve human judges.
Right, human judges.
Assessing the quality of the output.
Yeah, the coherence.
And then others use automated metrics.
Yes.
Comparing the model's performance to like a gold standard.
That's right.
So it's a combination of like human judgment and objective metrics.
Under good mix.
To get a comprehensive picture of what the model can do.
Exactly. The strengths and weaknesses.
Yeah.
And these evaluations.
Yeah.
They're crucial for tracking progress.
Yeah.
Identifying areas for improvement.
Right.
Making sure these models are, being developed the right way.
Right. In a way that aligns with human values.
Exactly.
But beyond these general evaluations.
Okay.
I'm also curious about like how we control and shape the outputs.
Yeah, that's a great question.
For specific tasks.
Uh-huh.
It's one thing to have a model that can generate like fluent text.
Right.
But how do we make sure it's generating the kind of text we want?
So there are several techniques for controlling the style and content of the model's output.
Okay.
One approach is to adjust parameters like temperature, top, during the sampling process.
Okay, those sound pretty technical.
They are a bit, yeah.
Can you break this down for me?
So think of it like adjusting the dials on a creativity machine. Temperature that controls the randomness of the model's output.
Okay.
So a higher temperature leads to more surprising and unpredictable results.
Okay.
Lower temperature makes the model's responses more deterministic, more focused.
So it's like choosing between like a jazz improvisation and a classical symphony.
I like that analogy.
Okay.
And top.
Yeah.
Those are like setting filters on the model's vocabulary, limiting the words it can choose from to create more focused, relevant responses.
So it's like giving the model a specific set of paints to work with.
Yes.
Instead of letting it use the entire color palette.
Exactly.
Okay.
And these techniques, they let us fine-tune the model's like personality, making it more creative, more formal, more humorous, whatever style fits the task.
So it's like we're conducting an AI orchestra.
Yeah.
Shaping the music.
Yeah.
To create the desired effect.
That's a great way to think about it.
Yeah. But sometimes we need more than just stylistic control, right?
Right. Sometimes you need structure.
Yeah. Sometimes we need to make sure the outputs follow a specific structure.
Especially when you're using LLMs as part of a larger system.
Like, think about using a language model to generate code.
Yes, good example.
You wouldn't want it to produce code with syntax errors.
Right, it has to be correct.
It needs to be structured properly to function.
Exactly.
I like that.
So that's where tools like Pydantic and Outlines come in.
Pydantic and Outlines, okay.
Yeah, they allow us to define specific schemas or templates for the model's outputs.
Okay.
Making sure it follows the desired structure.
So it's like giving the model a blueprint to follow.
A blueprint, yeah.
So it stays within the boundaries of the task.
Exactly.
Okay.
These tools, they let us harness the power of these language models while also maintaining control over their outputs.
Making have them more reliable.
More predictable.
For like real world use. This is incredibly valuable.
It is.
It's like we're, transforming these free-flowing language machines into these like precision instruments
so precise
that we can use to build complex systems and automate intricate tasks.
Powerful stuff.
But with all this talk about applications, I'm eager to hear more about how LLMs are actually being used.
Yeah, for sure.
In the real world.
Real world application.
They're more than just chatbots.
Yep, absolutely.
Okay.
Absolutely.
Yeah.
And one of the most exciting areas is prompting techniques.
Prompting.
It's all about crafting the right questions, the right inputs,
Okay.
to get the desired output from the model.
So it's like learning to speak the language of AI.
It is. It is figuring out how to ask the right questions.
Right.
To get the information or results you need.
Okay.
There's a real art to prompting.
Yeah.
It's a skill that's becoming more and more valuable in this age of AI.
Okay.
One popular technique is called few-shot prompting.
Few-shot prompting, okay.
Where you give the model a few examples of the desired output before giving it the actual task.
So it's like a quick tutorial.
A quick tutorial.
Showing it what you're looking for.
Exactly.
Okay.
And another powerful technique is called chain of thought prompting.
Chain of thought prompting, okay.
Where you guide the model
yeah.
through a step-by-step reasoning process.
So instead of just asking for the answer, you're walking it through the logic.
Yeah, walking it through.
The steps involved in getting to the solution.
Exactly.
This can be helpful for tasks that require, like, complex reasoning or problem solving.
Absolutely. It's like giving the model a thinking cap.
A thinking cap. Right.
Guiding it through that thought process.
This is fascinating.
It is.
It's like we're not just using these models as like black boxes, and we're collaborating with them.
Collaborating, yeah.
Shaping their thinking, guiding them towards these desired outcomes.
That's a great way to put it. Okay. And these prompting techniques,
they're
opening up all sorts of possibilities for using LLMs in these like creative and innovative ways.
I'm excited to see where it all leads.
Me too. Me too.
But one thing I keep hearing about is retrieval augmented generation.
RAG.
Yeah, okay.
It's all about connecting LLMs to external sources of information.
So it's like connecting their brains to the internet.
Exactly. Giving them access to this massive library of knowledge.
Right. So they're not just limited to what they've been trained on.
They can tap into all this information.
To answer questions, generate text, do tasks.
Yeah. It's incredibly powerful.
It's like giving them a superpower.
It is.
But how do we actually make that connection?
So this is where vector databases come in.
Vector databases. Okay.
Imagine you have a library with millions of books.
Okay.
But no card catalog.
Yeah.
No search system.
It would be impossible to find anything.
It would be a nightmare.
Yeah, like searching for a needle in a haystack.
Exactly. Vector databases.
Okay, we're back. Ready to wrap up our deep dive into generative AI.
Feels like we've explored a whole universe of concepts already.
We have, from the math all the way to the cutting-edge applications.
And there's still a few more fascinating areas to explore.
Really?
Yeah, before we wrap things up.
Okay, let's do it.
So, remember how we talked about efficiency?
Yeah, making these big models more efficient.
Right, especially when it comes to running them on, real-world hardware.
Right, because all this AI magic, it comes at a computational cost.
It does.
And as these models get bigger and more complex, we got to find ways to make them run faster, more efficiently.
We do, and that's where techniques like parameter quantization come in.
Parameter quantization. Okay, what's that about?
Think about how we compress files on our computer.
Okay, yeah.
To save space. Quantization does something similar for the parameters or weights of a neural network.
So it's like slimming down the model's code?
Yeah, kind of.
But without sacrificing its performance?
That's the goal.
Okay, that's pretty clever.
It's a neat trick.
It's like making these AI giants more lightweight.
Yeah, more agile.
Without, compromising their strength.
Exactly.
So what other performance optimization tricks do researchers have?
Well, there's this technique called speculative decoding.
Speculative decoding.
It's all about speeding up inference.
Inference, okay.
Think of it like having a junior writer create a rough draft.
Okay.
And then having a senior editor polish it up.
So it's a two-step process.
Yeah, 2 steps.
A smaller, faster model generates an initial output.
Right.
And then a larger, more accurate model refines it.
That's the idea.
Okay, so you're kind of like dividing and conquering the task.
Yeah, dividing and conquering.
Leveraging the strengths of different models.
Exactly.
To get that optimal performance.
That's it.
Okay.
And for speeding up the attention mechanism, which is like one of the most computationally expensive parts of a transformer model.
Okay.
There's this technique called flash attention.
Flash attention, that sounds fast.
It is fast, very fast.
Okay.
It's an algorithm that optimizes how attention is calculated.
Okay.
Reducing memory usage.
Yeah.
Speeding up the whole process.
Just like finding a shortcut
Yeah, a short
through a complex maze.
Exactly.
Making the model's, like, thought process more efficient.
More efficient, yeah.
Okay.
And then there are techniques like key value caching and page detention, which are all about avoiding redundant calculations.
So it's like remembering the answer to a question you've already asked.
Exactly.
Instead of having to, like, recalculate it every time.
That's the idea.
Okay.
These techniques can, like, really boost efficiency by storing and reusing those previously computed values.
So you're reducing the computational workload?
Reducing the workload, yeah.
It's fascinating how much of AI research is focused on finding these clever ways to optimize these models.
It's a constant challenge.
Yeah, it's like a race.
It is a race.
To make them faster.
Faster, smarter.
Faster, more efficient?
More efficient, all of that.
And as these models keep growing, these optimization techniques become even more crucial.
They do.
But one of the, I don't know, like, fundamental challenges with these large language models is, like, the way attention scales with the length of the input.
Right. The longer the input, the more computationally expensive it gets.
Right. So if you're trying to feed these models, like, really long documents or have them engage in, like, extended conversations, it can quickly become computationally prohibitive.
It can, yeah.
So what are researchers doing about that?
Well, there's a whole area of research focused on subquadratic context scaling.
Subquadratic context scaling.
It's a mouthful.
It is.
But basically, it means finding ways to make the computational cost grow less dramatically as the input length increases.
So it's like breaking the speed limit.
Yeah, breaking the speed limit.
Allowing these models to handle, like, longer and more complex inputs.
Exactly.
Without hitting that computational wall.
That's the goal.
Okay.
And there are some promising approaches.
Like what?
The one technique is called sliding window attention.
Sliding window attention.
Which is actually already used quite a bit.
Okay, how does that work?
Imagine you're reading a long book.
Okay.
You don't try to keep the whole book in your mind at once.
No.
You focus on a smaller window of text.
Right, like a paragraph or a page.
Yeah, and then you gradually shift your attention as you read.
So you're breaking down the task.
Yeah, smaller chunks.
More manageable chunks.
Exactly.
Okay.
Sliding window attention does the same thing for language models.
Oh.
It limits the model's attention to a smaller portion of the input at any given time.
So it's like giving the model a magnifying glass.
Yeah, a magnifying glass.
To focus its attention.
Focus its attention.
Okay.
And another interesting approach is called ring attention.
Ring attention.
Which involves dividing the input into blocks.
Okay.
And passing information between those blocks.
Okay.
In a ring-like structure.
So it's like a more structured and efficient way.
Yeah, more
to manage the flow of information.
Exactly.
Okay.
And then there's linear attention.
Linear attention.
Which is a technique for achieving subquadratic scaling.
Okay.
By leveraging the fact that a lot of the computations in these models can be expressed as linear transformations.
Linear transformations, that sounds familiar.
It should. We talked about something similar with embeddings.
Right, where words are represented as points.
Yeah, points in space.
In a high-dimensional space.
Exactly.
Right.
Linear attention builds on that concept.
So it's about finding ways to exploit
that underlying structure.
That linear structure.
Okay.
To make these models more efficient.
So it's like tapping into a hidden simplicity. Yeah, a hidden simplicity.
Within these complex systems to streamline the computation.
Totally streamlined, yeah.
Without sacrificing performance.
That's the goal.
Okay.
And one architecture that uses linear attention is called RWKV.
RWKV. Okay.
Which stands for Receptance Weighted Key Value.
Okay, that's a mouthful.
It is a mouthful.
But it's a hybrid model, right?
It is. It combines the strengths of RNNs and transformers.
Oh, wow. So it's taking inspiration from different approaches.
Taking the best of both worlds.
I like it.
Yeah.
But the handbook also mentions something called structured state space models.
SSMs. Yeah.
SSMs.
These are a bit more of a radical departure from the traditional transformer architecture.
Okay.
They're inspired by concepts from control theory.
Control theory?
And linear time invariant systems.
Okay. Those sound pretty advanced.
They are.
Okay, so like break it down for me.
The basic idea behind SSMs is to represent the model's internal state in a more compact, more efficient way.
Okay.
Which lets it process long sequences of information.
Okay.
Without running into that quadratic scaling problem.
So it's like finding a more elegant way.
Yeah, more elegant.
To represent the model's knowledge, its memory.
That's a good way to put it.
And SSMs, they've shown some pretty impressive results, right?
They have, especially in areas like text-to-speech synthesis.
Oh, wow.
Where there's been able to generate like incredibly realistic sounding speech.
That's amazing.
It is.
So they're not just a theoretical concept.
No, not all.
They're being used to build like real-world applications.
Real-world stuff.
Okay, but before we wrap up, I want to like zoom out for a second.
Yeah.
We've been talking a lot about language models.
We have.
But generative AI, it goes way beyond just text, right?
Absolutely. It's a much bigger world out there.
Yeah.
There are models that can create all sorts of things.
Like what?
Images, music, videos, even 3D models.
So we're talking about AI systems that can be creative. Creative, yeah?
Like they can be artists, musicians, filmmakers, even architects.
The potential is huge.
It's mind-blowing.
It is.
And a lot of these models,
yeah,
they're based on the same deep learning techniques.
Okay. That we've been talking about.
That power the language models.
Exactly, just applied to different domains.
So the same principles that allow a model to write a poem can also be used to, like, generate a painting. Or a piece of music.
Exactly. It's fascinating, isn't it?
It really is.
So one of the classic techniques for this is called a variational autoencoder.
VAE?
VAE.
Okay.
Remember we talked about autoencoders earlier?
Yeah.
VAEs are a special type designed for generating new data.
So it's like taking a blueprint.
Yeah, a blueprint.
And using it to create variations. New instances of that design.
That's a good analogy.
Okay.
VAEs learn a compressed representation of the data.
Which captures those essential features, the patterns.
Right.
And then they use that representation to generate new samples.
Okay.
That resemble the original data.
So it's like learning the essence of a data set.
Yeah, the essence.
And then using that essence to create something new.
New and unique.
Okay.
VAEs have been used for all sorts of things.
Like what?
Generating realistic images of faces.
Okay.
Creating new musical melodies.
That's wild.
It is.
But I've also heard about generative adversarial networks.
GANs.
GANs.
Yeah, GANs are really clever.
Okay.
They involve training two neural networks against each other.
Against each other.
Yeah.
Okay.
One network, the generator, tries to create realistic data.
Okay.
The other network, the discriminator, tries to tell the difference between real and fake data.
So it's like a game of cat and mouse.
It is. It is.
The generator's trying to fool the discriminator.
Yeah.
The discriminator's trying to catch the generator out.
Exactly.
Okay.
And as they train, they both get better.
Okay.
The generator learns to create more realistic data.
Okay.
The discriminator gets better at spotting fakes.
So the competition drives innovation.
It does. It pushes them both to improve.
Okay.
And that's how you get those, like, hyper-realistic images.
Right, because the generator's constantly trying to create things that the discriminator can't tell apart from the real thing.
Exactly.
Okay, so are GANs only used for images?
No, they can be used for other types of data.
Okay.
But they've been super successful with images.
Yeah, I can see why.
Those fake images, they're so convincing.
They are.
But GANs can also be used to generate images from text prompts.
That's what DALL-E and Midjourney use, right?
That's right.
Okay.
Those tools use a type of GAN called a conditional GAN.
EDGAN.
Or CGAN.
Okay, so what makes them different?
So CGANs are trained on pairs of data.
Okay.
Like images and their captions.
Okay.
This lets them learn the relationship between text and images.
So they can generate an image from a description.
Exactly. It's like giving the model instructions in text.
Okay.
And it uses those instructions to paint a picture.
That's incredible.
It is.
The handbook also mentions normalizing flows.
Oh, right. Normalizing flows.
What are those all about?
These are a bit more technical.
Okay.
But they're another powerful technique for generative modeling.
Okay.
They involve learning a series of transformations that can be applied to a simple distribution, like a Gaussian distribution, to create a more complex, more interesting distribution.
So it's like taking a simple shape.
Yeah.
And twisting and turning it.
Twisting and turning.
To create something more elaborate.
Exactly.
And by, like, carefully designing these transformations, you can create models that can generate all sorts of complex data.
All sorts.
Images, audio, even molecular structures.
It's pretty amazing.
It is. It seems like the possibilities are endless.
It does feel that way sometimes.
Shh. Yeah.
But one technique that's been, like, making headlines lately is diffusion models.
Diffusion models, okay.
They're behind those amazing images from Stable Diffusion.
Right, Stable Diffusion, yeah.
Diffusion models are a relatively new approach.
Okay.
And they've been getting some incredible results.
Okay, I'm all ears. How do they work?
So imagine you have this beautiful painting,
Okay.
and you slowly add noise to it,
Okay.
gradually corrupting the image until it's just random pixels.
Okay.
A diffusion model learns how to reverse that process,
Okay.
starting with pure noise
Yeah.
and then gradually refining it.
Step by step.
Step by step.
Until it turns into a coherent image.
Exactly.
So it's like taking a shattered vase
Yeah.
and painstakingly piecing it back together.
That's a great analogy.
Okay.
And what's key here is that these diffusion models, they learn to denoise the image in a guided way,
Okay.
using the text prompt as a guide.
So the text prompt is like a blueprint,
A blueprint, yeah.
guiding the model to create that specific image.
Exactly.
That's really cool.
It is, and they've been super successful
Yeah.
at generating high-quality images from these prompts.
It's mind-blowing.
It is. It's an incredibly dynamic field.
It really is. It seems like every day
Yeah.
there's a new breakthrough pushing the boundaries
Pushing the boundaries. That's AI.
of what's possible.
It's exciting.
It is, but as we move towards like more sophisticated systems, it becomes even more important to understand how they work
How they work, yeah.
and how to ensure they're used responsibly.
Absolutely. Responsibility is key.
But there's one final area I wanted to touch on.
Okay.
Multimodal models.
Multimodal models, yes.
Okay, this sounds like we're stepping into the future.
We are. This is where things get really interesting.
Okay.
So multimodal models are AI systems
Yeah.
that can handle multiple types of input and output.
Multiple types, like what?
Text, images, audio, even video.
All processed by a single model.
A single model. That's the idea.
That's like, I don't know, an AI that can see, hear, speak, understand language all at once.
It's like something out of science fiction,
It really is.
but it's an area of active research
Okay.
with incredible potential.
Okay, I got to share more about this. What are the key ideas here?
So one important concept is tokenization beyond text.
Okay, we talked about tokenization for language models.
Right. Breaking down
Yeah.
text.
Yeah.
But we can apply similar techniques
Okay.
to audio, images, video,
Okay.
creating tokens that represent different aspects of those modalities.
So it's like a universal language for AI.
I like the idea.
Different types of data
Yeah,
represented and processed in a unified way.
exactly.
Okay.
And there are some promising architectures,
Like what?
VQVAE,
Okay.
which is popular for image generation,
Okay.
and vision transformers,
It is transformers.
which are designed to handle visual information.
So we're seeing models that can blend different types of data,
Yeah, blend them seamlessly.
creating new possibilities.
New possibilities,
Lots of
yeah.
applications.
And one exciting area
Yeah.
is generalized visual language models,
Okay.
or GVLMs.
DVLMs.
They're trained on huge data sets of text and images,
Okay.
so they can understand the relationship between the two
Okay.
and generate new content
Yeah.
that blends both.
So it's like an AI that understands words and pictures
Exactly.
and can create new forms of expression,
New forms of expression.
combining both.
It's pretty amazing.
This has been an incredible deep dive.
It has.
I feel like I've learned so much
Good.
about this like rapidly evolving field.
It is rapidly evolving.
What advice would you give to our listeners
Oh, that's a good question.
who are like eager to learn more,
Yeah.
maybe even contribute to this field?
So my advice would be stay curious, keep exploring.
Okay.
Don't be afraid to get your hands dirty.
Yeah.
There's so many resources out there. Tutorials, blog posts, open source code, data sets.
It's all out there.
It's all out there.
And who knows, maybe one of our listeners will make the next big breakthrough.
It's possible.
It's possible.
But even if you're not, building the next big AI,
yeah.
just understanding these technologies, their implications, it's becoming more and more important for everyone.
Absolutely. AI is already shaping our world.
It is.
And its influence is only going to grow.
It will.
So we all need to be informed
Yeah.
and engaged in the conversation.
About how we shape the future of AI.
Yeah, the future of AI is in our hands.
It is. It is.
That's a great note to end on.
Thanks.
Thanks for joining us
It's been a pleasure.
on this incredible journey.
A fascinating journey.
And we'll see you next time.
See you next time. For another deep dive into the world of knowledge and ideas.